satellite management task, which also involves an earth station dedicated to the task and a group of personnel. The main function of the satellite management are to control the orbit and altitude of satellite, monitor the status of all sensors and subsystems of satellite, and then switch on and switch off sections of communication systems. The TTC and M Earth station may be owned or operated by the satellite owner, or it may be owned by the third party and provide a TTC and M service under contract. On large geostationary satellites, some repointing of individual antennas may be possible under the command of the TTCM system. Tracking is performed primarily by the Earth station. Figure illustrates all function of the controlling Earth station. Telemetry and monitoring system. The monitoring system collects the data from the sensors within the satellite and sends this data to the controlling Earth station. There may be several hundred sensors located on the satellite to monitor pressure in the fuel tanks, voltage and current in the power conditioning unit, current drawn by each subsystem, and critical voltage and currents in the communication electronics. The temperature of many of the subsystems is important and must be kept within the predetermined limits, so many temperature sensors are fitted. And the sensor data, the status of each subsystem, and the positions of the switches in the communication system are reported back to the Earth by telemetry system. The sighting devices used to maintain the altitude are also monitored via the telemetry link. This is essential in case one should fail and cause the satellite to point in the wrong direction. The faulty unit must then be disconnected and the space brought into the command system or some other means of controlling attitude device. Telemetry data are usually digitized and transmitted as a phase shift keying of a low power telemetry carrier using time division technique. A low data rate is normally used to allow the receiver at the earth station to have a narrow bandwidth and thus maintain a high carrier to noise ratio. The entire TDM frame may be contain thousands of bits data and take several seconds to transmit. At the controlling earth station, a computer can be used to monitor, store, and decode the telemetry data so that the status of any system or a sensor on the satellite can be determined immediately by the controller on the earth. Alarms can also be sounded if any vital parameter goes outside the allowable limits. Tracking. A number of techniques can be used to determine the current orbit of satellite. Velocity and acceleration sensors of the satellite on the satellite can be used to establish a change in the orbit from the last known position by the integration of data. The Earth station controlling the satellite can observe the Doppler shift of the telemetry carrier or a beacon transmitter carrier to determine the rate at which the range is changing. Active determination of range can be achieved by transmitting a pulse or sequence of pulses to the satellite and observing the time delay before the pulse is received again. The propagation delay in satellite transponder must be accurately known, and more than one Earth station may make range measurement. If a sufficient number of Earth stations with adequate separation are observing the satellite, its position its position can be established by a triangulation from the Earth station by simultaneous range measurement. With a precision equipment at the Earth station, the position of satellite can be determined within 10 meters. Ranging tones are also used for range measurement. A carrier generated on board the satellite is modulated with a series of sine waves at increasing frequency, usually harmonically related. The phase of the sine wave modulation components is compared at the Earth station and the number of wavelengths of each frequency is calculated. Ambiguities in the number are resolved by the reference or to lower frequencies and prior knowledge of the approximate range of satellite. If sufficiently high frequencies are used, perhaps even the carrier frequency range can be measured to millimeter accuracy, and the technique is similar to that used in a terrestrial telorometer meter and in aircraft radar altimeters. Command. A secure and effective command structure is vital to the successful launch of operation of the satellite of any communication satellite. The command system is used to make changes in attitude and corrections to the orbit and control communication system. During launch, it is used to control the firing of the apogee kick motor and to spin up a spinner or extend the solar sails and antenna of the three-axis stabilized satellite. The command structure must possess safeguards against the unauthorized attempt to make changes to the satellite's operation and also against the inadvertent operation of a control due to the error in the received command. Encryption of commands and responses is used to provide a security in the command system. A typical system of a type is shown in the figure that will originate the command at a control terminal of the computer. The control code is converted into the command word, which is then sent in TDM frame to the satellite. After checking for validity in the satellite, the word is sent back to the control station via the telemetry link where it is checked again in the computer. It is found and have been received correctly, and execute instruction will be sent to the satellite so that the command is executed. The entire process may take 5 or 10 seconds but minimizes the risk of erroneous command and causing a satellite malfunction. The command and telemetry links are usually separate from the communication system, although they may be operate in a same frequency band 6 and 4 GHz. Two levels of command system are used in the Intelsat satellite. The main system operates in a 6 GHz band in a gap between the communication channel frequencies. The main telemetry system uses a similar gap of 4 GHz band. The TTC antennas for the 6 by 4 GHz system during the launch phase and injection into the geostationary orbit. The main TTC and M system may be inoperable because the satellite does not have the correct attitude or has not extended its solar cells. A backup system is used at this time which controls only the most important section of satellite. A great deal of redundancy is built into this system since its failure will jeopardize the entire mission. Near omnidirectional antennas are used at either UHF or S band, that is 2 to 4 GHz, and sufficient margin is allowed in a signal to noise ratio SYN at the satellite receiver to guarantee control under the most adverse conditions. The backup system provides control of a apogee kick motor and attitude control system, orbit control thrusters, the solar cell deployment mechanism, and the power conditioning unit. With these controls, the satellite can be injected into the geostationary orbit, turned to face the Earth, and switched to full electric power so that handover to the main TTC and M system is possible. In the event of failure or the main TTC and system, the backup systems can be used to keep the satellite on station. It is also used to eject the satellite from geostationary orbit and to switch off all transmitters when the satellite eventually reaches the end of its useful life. Power system. All communication systems satellites obtain their electrical power from the solar cell, which convert incident sunlight into the electrical energy. Some deep space planetary research satellites have used a thermonuclear generator to supply the electrical power. But because of the danger to people on Earth, if the launch should fail, the nuclear fuel be spread out over the inhabited area. Communication satellites have not used nuclear generator. The sun is a powerful source of energy. In a total vacuum of outer space at geostationary altitude, the radiation falling on the satellite has an intensity of 1.39 kilowatt per meter square. Solar cells do not convert all the incident energy into the electrical power. Their efficiency is typically 20 to 25% at the beginning of life, but falls with time because of aging of cells and etching of the surface by micrometer impacts. Since sufficient power must be available at the end of life, the satellite to supply all the system on board. About 15% extra area of solar cells is usually provided as an allowance for the aging. The spin-stabilized satellite usually has a cylindrical body converted in solar cells. Because the solar cells are on the cylindrical surface, half of the cells are not illuminated at all, and at the edges of the illuminated half, the low angle of the incidence results in a little electrical power being generated. The output from the solar cells is slightly higher than obtained with a normal incidence on a flat panel equal in area to the projected area of cylinder, that is the width times its height. The cells that are not illuminated by sunlight face cold space, which causes them to cool down. The solar cells on a spinner satellite have a lower temperature than those on the solar cells, which increase their efficiency somewhat. Early satellites were of a small dimension and had relatively small areas of solar cell. Recently, large communication satellites for direct broadcast operation generate up to 6 kW from solar power. A three-axis stabilized satellite can make better use of the solar cell area, since the cells can be arranged on flat panels that can be rotated to maintain the normal incidence of the satellite. Only one-third of the total area of solar cells is needed relative to the spinner, with some saving in width. A primary advantage, however, is that by unfurling a folded solar array, when the satellite reaches geostationary orbit, power in excess of 10 kW can be generated with large arrays. To obtain 10 kW from the spinner requires a very large body on which to place the solar cell, which may then exceed a maximum payload dimension of a launch vehicle. Solar cells must be rotated by an electric motor once per 24 hours to keep the cells in full sunlight. This causes the cells to heat up typically to 50 to 80 Celsius, which causes a drop in the output voltage. In the spinner design, the cells cool down when in shadow and run at 20 to 30 Celsius with somewhat higher efficiency. The bombardment of the cells by protons and electrons is also more severe, and the thicker layer of the glass may be needed to slow down the deterioration of the cell, with a consequent weight penalty. A rotary joint must be used with each solar cell to transfer current from rotating cell to body of the satellite. The satellite must carry batteries to power the subsystems during a launch and during eclipse. Eclipses occur twice per year, around the spring and fall equinox, when the Earth's shadow passes across the satellite. The longest duration of eclipse is 70 minutes, occurring around 21st March and 21st September each year. To avoid the need for the large and heavy batteries, part of the communication system load may be shut down during eclipse. But this technique is rarely used
when the telephony or the data traffic is carried. TV broadcast satellites may not carry sufficient battery capacity to supply their high power transmitter during eclipse and may shut down. By locating the satellite 20 degrees west of the longitude of the service area, the eclipse will occur after 1 am local time for the service area when shutdowns is more acceptable. Batteries are usually of the nickel hydrogen type which do not gas when the charging and have good reliability and long life and can be safely discharged to 70% of their capacity. A power conditioning unit controls the charging current and dumps excess current from the solar cells into the heaters or load resistors on cold side of satellite. Sensors on the batteries, power regulator and solar cells monitor temperature, voltage and current and supply these data to both the onboard control system and controlling earth station via the telemetry downlink. Typical battery voltages are 20 to 50 volt with capacities of 20 to 100 ampere hour. Communication subsystem. A communication satellite exists to provide a platform in geostationary orbit for the relying of voice, video, and data communication. All other subsystems on the satellite exist solely to support the communication system, although this may be represent only a small part of volume, weight, and cost of satellite in orbit. Since it is a communication system that earns the revenue for the system operator, communication satellites are designed to provide the largest traffic capacity possible. The growth in capacity is well illustrated in figure for the Intelsat system. Successive satellites have become larger, heavier, and more costly, but the rate at which the traffic capacity is increased has been much greater, resulting in a lower cost per telephone circuit or transmitted bit with each succeeding generation of satellite. The satellite transponders have limited output power and a station at 36,000 km away from a geo satellite, so that received power level even with a large aperture or station antennas is very small and rarely exceeds to 10 raised to minus 10 watt. For the system to perform the satisfactorily, the signal power must exceed the power of the noise generated in a receiver by between 5 and 25 dB, depending on the bandwidth of the transmitted signal and the modulation scheme used. With a low power transmitter, narrow receiver bandwidths have to be used to maintain the required signal to noise ratio. Early communication systems, satellites, were fitted with the transponders 250 or 500 MHz bandwidth but had low gain antennas and transmitters of 1 or 2 watt output power. The earth station receiver could not achieve adequate signal to noise ratio when the full bandwidth was used, with a result that the system was power limited, and later generations of a communication satellite have a transponders with greatly increased output power up to 200 watt for a DBS TV satellite and a steadily improved in the bandwidth utilization efficiency. We can see this in figure. The total channel capacity of a satellite that uses a 500 MHz band at 6 by 4 GHz can be increased only if the bandwidth can be increased or reused. The trend in the high capacity satellite has been reuse the available bands by employing the several directional beams at the same frequency, spatial frequency reuse, and orthogonal polarization at the same frequency reuse. Large GEO satellites also use both 6 by 4 GHz and 14 by 11 GHz band to obtain more bandwidth. For example, some GEO satellites have achieved an efficient bandwidth of 2250 MHz within the 500 MHz band at 6 by 4 GHz and a 250 MHz band at 14 by 11 GHz by a combination of a spatial and polarization frequency reuse. And later generations of an Intelsat satellite have achieved up to the sevenfold reuse of their frequency bands. The designer of satellite communication system is not free to select any frequency and a bandwidth he or she chooses. International agreements restrict the frequencies that may be used for particular services and regulations and administered by the appropriate agency in each country. The Federal Commission (FCC) in United States. The bands currently used for the majority of service are 6 by 4 GHz and 14 by 11 GHz, with 30 by 20 GHz coming into service. The 6 by 4 GHz band was expanded from 500 MHz bandwidth in each direction to 1000 MHz by a World Administrative Radio Conference in 1979. But other services share the new part of the band and may cause the interference to the satellite communication link. Similar bandwidth is available at 14 by 11 GHz, and Ka-band satellite will be launched into the first decade of 2000 to exploit the wider bandwidth available into a 30 by 20 GHz band. The different frequency is required to the transmit path normally at the higher frequency at the satellite because the high power transmit signal would overload the receiver if they both operated at the same frequency. The 500 MHz bands originally allocated for 6 by 4 and 14 by 11 GHz satellite communications have become very congested and now completely filled for the some segments of the geostationary orbit, such as that serving North America. Extension of the bands of 1000 MHz will eventually provide a greater capacity as the new frequencies come into use. Many systems now use 14 by 11 GHz for TV broadcast and distribution, and 30 by 20 GHz systems are introducing Internet-like services from GEO. The standard spacing between the GEO satellite was originally set at 3 degrees, but under regulations covering North America and much of the rest of the world, the spacing has been reduced to 2 degrees. The move to 2 degree spacing opened up extra slots for new satellites in the 6 by 4 and 14 by 11 GHz band. Satellite systems designed for Ku band 14 by 11 GHz and Ka band 30 by 20 GHz have narrower antenna beams and better control of coverage patterns than a satellite using a C band 6 by 4 GHz. As available orbit slots for GEO satellites have filled up with satellites using the 6 by 4 and 14 by 11 GHz, attention have focused on the use of the 30 by 20 GHz band. Originally, this band had 3 GHz bandwidth allocated to the satellite services, but part of the band was reallocated to the Land Multipoint Distribution Service (LMDS). Approximately 2 GHz of bandwidth is still available for satellite systems at Ka-band on the exclusive or shared basis, which is equal to the combined allocation of C and Ku bands. However, propagation in rain becomes a major factor at frequencies about 10 GHz. Attenuation in rain increases at roughly the square of the frequency. So at 20 GHz, rain attenuation is 4 times larger in dB than at 10 GHz. It is almost impossible to provide a rain attenuation margin larger than 20 dB in any system, and mainly Ka-band systems will have a margin of only 4 to 5 dB when operating to a small earth station antenna.